All right, so what I'm going to do is pick up more or less where I left off. So we have this Bayer propagator. Before lunch, we calculated this self-energy. So when we put this together, we're going to get a dressed propagator for this P-wave dimer that looks like I, because both the self-energy and the Bayer propagator are diagonal. The dressed propagator is also diagonal. And then we're going to have the parameters of the theory minus the self-energy. And writing this with malice aforethought in terms of where I want to go for renormalization, I'm going to write this as this, I claim, is what you get if you substitute this result into here for sigma pi, and then I multiplied the top and the bottom by 6 pi over mr g squared in anticipation of getting that overall factor of 6 pi mr over there. So now, what do I have to do in order to turn this into an amplitude? This is the dressed dimer, right? So in order to turn this into an amplitude, I need to I want the scattering amplitude, right? So if I want the scattering amplitude, I need to turn this into something that tells me how a neutron and a core come in and go out. So what do I need to attach here? Vertex on the front and the back, right? So this vertex is going to give me the incoming momentum, and this vertex is going to give me the outgoing momentum. I should have put a pi here. So this implies an amplitude which is minus 6 pi over mr, the factors of g pi cancel, I, a prime, sorry, no I got rid of them, a prime dot k, and then this combination, actually I will do it off with the order, 6 pi delta pi over mr b pi squared plus okay. So if I did this right, this combination here in PDS, I should say in PDS, this combination here is going to be minus 1 over A1. Let me see if that's what I wrote in my notes. Okay. And actually, it's going to be plus 1 over 1. No, it's going to be, okay. I think I have oh, it's this, okay, yep, good. Okay, it's going to be plus 1 over A1. This because what I keep sweeping under the rug, but maybe now I need to tell you out loud, is that this A is equal to minus this scattering amplitude over here, because particle physicists and nuclear physicists use opposite conventions for the scattering amplitude. Nuclear physicists like to have a scattering amplitude whose sign is the same sign as the potential energy. I think that makes sense myself. Particle physicists like to define because they want V to be associated with a Feynman rule that comes from the Lagrangian, and in the Lagrangian, V has a minus sign, right? So, okay, so this one is going to have an overall opposite sign to this one. Okay. Of course, none of this matters if you're going to square it, but it does matter in terms of signs if you're going to do matching. So, all right, so I finally fessed up to this, having managed to bury it under the rug the whole of the week, but it's probably a useful thing for you to know if you're going to read nuclear physics literature. All right, so with that in mind, this is equal to plus 1 over A. All of this stuff is equal to minus a half R1. And then once we take account of this overall minus sign, this plus IK cubed matches. Because it's a plus IK cubed once I pull through the minus sign over there. All right, any questions? All right, so at this point, you're like, this is great. Everything is done. We calculated the leading order amplitude in P waves. And then you go and look at experimental data for a bunch of these systems. And you realize, or if you prefer pure thought, you realize that you have the following problem, that since you have you have 2 parameters at leading order, and you're trying to get the denominator to go to 0, you're going to have to do you have to think about how you want to achieve your low energy state. So you could demand that all terms in the denominator have the same size. So in that counting, 1 over A1 would be of order the low scale. Let's call it binding momentum cubed because it has third order in momentum. R1 would be of order gamma, and then all 3 terms have the same size, right, at low momentum, because the third term is a K cubed. But this, you can already see, this requires you to fine-tune 2 different low energy parameters in the theory. It requires you to somehow arrange things so that 1 over A1 is unnaturally small and R1 is unnaturally small. We'll come back to whether this is actually possible. There's a different way to get a low energy bound state or resonance, which requires less fine-tuning, because we just assume that R1 has its natural size, lambda, and then we're going to look for the special point where these 2 terms cancel. So as long as the signs work out, I can always find, actually, even if the signs don't work out, so I can always find either a resonance or a bound state such that these 2 terms cancel as long as 1 over A1 has this size. Because as long as I, for the moment, don't think about the third term, this thing is going to have a 0 somewhere. So this is the counting I'm going to pursue here. And there's a physics reason for that, which is that just as there's an expectation for the size of the effective range in S waves, there's an expectation for the size of the effective range in P waves. In a single channel problem, there's actually a bound, just as there is for S waves, right, that R1 should be negative and R1 should be of order minus 1 over the range of the potential. So this counting that R1 should be of order lambda is natural. I mean, it's not just natural, it's inconsistent with known things from scattering theory. So this has taking this counting has the following consequence. So now when we look at, if we look at our dressed dimer propagator, or actually even better, if we look at the amplitude, the particle physicist amplitude is minus 6 pi over mr So the size of these terms, this one is of order lambda squared gamma. This one is of order lambda gamma squared. This one is of order lambda k squared. And this one is of order k cubed. So this term is actually small compared to these two. So this actually is different to something we talked about this morning. When we talked about S waves, I said you can never see the bare dimer because it has, you have to sum all loops at leading order. But if this is the counting here, then in fact, these two terms in the denominator are most of the time, dominant over this term. And I can do geometric series in ik cubed over minus 1 over a1 plus 1/2 r1 k squared. So what does that mean? That means I want to do geometric series in the, if you like, in the finite part, at least in the unitarity part of the dimer bubble. So this thing is of order 1 over lambda k squared, let's say. And then this is 1 over lambda k squared. The unitarity piece is k cubed, and this is 1 over lambda k squared. So I think hopefully you can see that every time we include another bubble, if this is indeed the scaling of the parameters in a dimer propagator, that R1 scales like lambda and 1 over A1 scales like this, then every time we add another bubble, we go down by a power of k over lambda. Now, there is one kinematic regime that's an exception to this. So when can't I make this geometric series? Like, what would have to happen to the denominator for that to become a silly thing to do? Yeah, that's right. So if the modulus of this gets smaller than this, then in other words, if this parameter becomes larger than 1, then I shouldn't make this expansion. Right. So let's think about the following situation. Let's suppose that so let's consider I'll just make A1 equal to, what do I want? I want 1 over 2 times R1 times the absolute value of R1 gamma squared. And then if I think about 1 over A1, but then if I think about this combination, remembering that R1 is negative, I analytically continue to where I expect to find a pole. And then this k squared becomes minus gamma squared, and R1 is negative. So R1 is equal to minus the absolute value of R1. So this blows up. So in other words, if I turn this around, I can say that I expect to find, so if A1 is positive, this has a pole at k is equal to I gamma with gamma equal to the square root of 2 over A1 times the absolute value of R1. And if you're near the pole, this counting that I did over there breaks down. If A1 is negative, then there's a pole is the same magnitude, but now it's real. So I would say at K equals to KR, with KR equal to the square root of 2 over A1 R1. So what's that? That's, I have some phase shift, let's say, and this thing is going to blow up. It's going to just blow up like this. Okay, but we know, I mean, maybe you've seen, maybe if I square it, if I talk about, crudely speaking, about the cross sections, be just the cross section associated with P waves, then it's going to be do this. So this, to sort of close the circle here, looks a lot like what you would see if you solved the harmonic oscillator, but you didn't damp it. If you solved the driven harmonic oscillator, I should be careful, and you didn't damp it. So this phenomenon here, many of you will be familiar with, this means that we have a resonance at this place. And what this, all this power counting stuff is telling us is that if you're near the resonance, you need to resum the unitarity correction. You need to resum the width. So let me repeat the argument. So the argument is, if I'm far away from the resonance, in other words, if I'm in a situation where 1 over A1 minus 1/2 K squared R1 is much larger than K cubed, as long as this is true, then this dominates. But if I'm near a point where this equals 0, and whether that equals 0 in the scattering regime or the bound state regime depends on the relative sign of R1 and A1, right? But if I'm near a point where this combination equals 0, if 1 over A1 is approximately 1/2 R1 K squared, like that. And in that, and then what's going to happen is that this curve is not going to look like this. It's going to look like, become some sort of Breit-Wigner type resonance form. Okay. So this is an interesting EFT. It's not as simple or as satisfying as the S-wave EFT, because you can't just declare that you have a single power counting in the whole kinematic regime. And you also have this phenomenon that, in addition, the scattering is weak down here. It's not as weak as if things were fully perturbative in the P waves, but it is of order K divided by lambda. But there is a place where the scattering becomes strong, and that's the place where the resonance occurs. And when that happens, you have to resum the unitarity corrections. So just to make this point explicit from the effective range expansion, if I have K cubed cotangent delta 1 equals 1/2 R1 K squared minus KR squared, then cotangent delta, unless the thing in round brackets is small, as long as K is small compared to my high scale associated with the range of my interaction, this thing will be big. Cotangent delta big means delta small. But if this happens to be close to 0, that can offset the bigness of this. If this is, there will be a point when this goes to 0, and when this goes to 0, delta goes through 90 degrees, which is the characteristic signature of a resonance. And then obviously, you can't expand in ik cubed over k cubed cotangent delta if k cubed cotangent delta is approximately 0, which is what happens at a resonance. So I'm going to tell you that this is actually a general effective field theory for resonances. So you can, I've played this game with several resonances now, starting with the delta, moving on to these P-wave halo resonances, and then in other contexts too. This sort of counting essentially always works for a narrow resonance. Right? That the loop corrections are perturbative if you're off resonance, but they need to be resummed using a Dyson equation, because if you get on resonance, because then the propagator diverges, and then you need the Dyson, that basically mandates that you sum everything in the Dyson series because it's all the same order. Right, so, and then I will just write down without, because we've had enough calculation over the last few days, so I will just write down without going through the calculation. If you, for bound states, that was the discussion for resonances. If you happen to have a shallow P-wave bound state, like in beryllium 11, then if you want bound state properties, then you need, if you, for instance, if you want to consider a process involving a P-wave bound state, then you have to live at the pole. And if you're at the pole, by definition, all three terms contribute, because at the pole, the denominator is 0. So you also need to resum there. And so, as I was discussing yesterday, the simplest way to find out properties of the bound state is to look for poles of the propagator. So going back to our expression, if you take our expression and you play the same game we played yesterday of converting it to something that looks like that's a Laurent expansion, then you discover this for the propagator, and this where B is the binding energy. This is gamma, so B is 1 over 2 MR times 2 over A1 mod R1. Yep. And so you can identify this combination of things as the wave function renormalization for this field. Sorry, with a minus sign. Now, you might be horrified that the Z pi has a minus sign in it, and you would be right to have some concerns. So let me make sure that the minus sign features prominently, just so I fully make you confront your horror. But this actually tells you that if this theory is going to be sensible, R1 better be negative. Right? So you're actually getting a constraint on whether this state is physical or not. The state can only be physical if the propagator has a positive residue. Otherwise, it's like a ghost state. You can't normalize the state in quantum mechanics if it has a negative residue, because you can't take the square root of that. So if you think about this as what you do, it's like if you computed the wave function squared and you got a negative number, you'd be like, well, that's weird. What's up with that state, right? So that's what's going. So this actually puts constraints on R1. It not only says that R1 needs to be negative, but it says that the absolute value of R1 needs to be larger than this, so that this whole combination is negative. So that it puts bounds on where it's sensible to treat the problem in this way. Okay, and that is all I have to say about P waves. All right. So questions about P waves. And I'm going to set up the problem of solving for the scattering of 3 particles, and then I'm going to make you do an exercise. And then we're going to be done. Okay, yes? No, R1 doesn't. This combination does. R1 is a number that's measured in experiment. Yes. So you need to absorb the mu dependence into this parameter, right? So just like, so if we did this using a cutoff, then this parameter, like delta pi over g pi squared, would need to absorb a lambda cube divergence. And then this parameter, y pi over g pi squared, would need to absorb the lambda divergence, right? So this is just saying that this has that y pi blah, blah, blah is equal to like, I think it's minus a half R1 minus 3/2 mu PDS. Yeah. Again, right, there's actually this causality bound business is actually hiding in here. So because this is a positive number and mu is a positive number, otherwise the PDS thing doesn't make sense. And all of that is equal to minus a half R1. Right? So there's a hint here already, right, that unless you're willing to make, if you want y to be positive, like last time we got away with this by just making y negative, but if you want y to be positive, then R1 better be negative. And moreover, R1 will be of order mu. So if you set mu, if you chose to set mu at that, I don't think it, like then that messes up certain power counting aspects. But if you did choose to set mu at like the natural scale lambda, then R1 would be of order lambda. So this is actually related to Professor Kaplan's thing about, you know, being able to naive dimensional analysis, being able to estimate the size of counter terms by estimating that things will take on the size of quantum corrections at the natural scale. If that is the simplest thing you can assume, or the most natural thing in the particle physics language. Other questions? Yeah, yes, I think so. I mean, I'll be honest, right? This number is not as easy to interpret as the effective range in S waves. But I will say that if you try this for a bunch of different potentials, you'll find that typically it's of order minus 1 over the range of the potential. If you take the range of the potential, there's a theorem, right? If you take the range of the potential to 0, R1 is forced to minus infinity. Other questions? All right. So let me clean some board. So don't worry, I'm not going to solve like a whole 3-body problem today, but I'm attempting to get myself in a position to finish my lectures tomorrow by deriving a set of a set of integral equations for 3-body scattering. And then I will do a little bit of analysis of their properties. But Professor Kirscher, who is arriving Friday, and will be lecturing next week, is going to do a detailed analysis of the properties of such integral equations. But you might ask, why do we need an integral equation? So in the next 30 minutes, together, we will figure out why we need an integral equation. And we're going to talk about dimers, because that's what we do here. All right. Okay, so first, a little motivation. So I'm interested in systems composed of 2 neutrons and a core. So what are some examples of this? Lithium-11, which is the first halonucleus ever discovered, by the way. It was discovered by Tanihata et al. They were measuring the radii of different lithium isotopes. And they the radii just went up nice and like 8 to the 1/3, and suddenly lithium-11 had a much larger radius than lithium-9. And we're like, well, that's interesting. Carbon-20, the triton, beryllium-14, and boron-19. So what all these nuclei have in common is, number one, that they're neutron rich, right? They have a neutron to proton ratio that is larger than 1. And number two, actually, it's not true that all of them are the last strongly bound isotope, because, for instance, there's carbon-22. But the other thing that they have in common is that they all have a small 2-neutron separation energy. In other words, it doesn't take much to liberate the 2 neutrons out of the nucleus. So let me do some, this colored chalk thing is really great. So this one, and this one, and this one, the circled ones, these are Borromean systems, named after the Borromean rings, which is the coat of arms of a family in northern Italy, which were 3 interlocked rings. And if you removed any one of the rings, the whole thing fell apart. It was meant to symbolize the way that the family connections were supposed to work, right? We are all essential. If you remove any one of us, it falls apart. So these Borromean systems are so called because in these systems, so let's take lithium-11. I'm going to think about this like this. So 2 neutrons are not bound. Lithium-10 is also not bound. So none of these 2-body subsystems is bound, but if you bring all 3 of them together, then they're bound. We all have friends like this, right? It's like, if it was if you and friend A got together, it wouldn't be fun. If you and friend B got together, it wouldn't be fun. But if you and friend A and friend B get together, then it's fun, right? So you hope that it's also true that friend A and friend B feel that it's not fun if they get together without you. All right. So anyway, so this is a Borromean system. So is this, so is this. And some of the binding energies here are kind of remarkable, right? So in this one, there's a resonance. So boron-18 is not bound, but it has a low energy S-wave resonance at 5 keV. And boron-19 itself is bound by 90 keV. These are extremely fragile nuclei. You can make your own joke here about fragile nuclei. Perhaps it's, they're Borromean, right? So like, it doesn't take much to mess up the relationship and break it all apart, right? They're extremely fragile nuclei, and they are, just as with the 2-body case, this is a quantum phenomenon, right? These would not be bound if you just considered the classical system. And just as with the 2-body case, there are analogs in atomic physics of these Borromean 3-body systems. All right, so these things are not Borromean because the deuteron is bound and carbon-19 is bound, but these are not bound by much, so these are also so-called 2-neutron halos. So what I'm going to do is introduce an NN dimer, which I'll call T, or isospin triplet, and an NC dimer, which I'll call D for dimer. Also because if, like I told you, you can make C the proton. If you make it the proton, then the NC dimer is the deuteron. So diagrammatically, the DRESS neutron-neutron dimer is going to look like this. I wanted to call it the dineutron, which is because that's really what it is, but then they'd both be D, and that would be very confusing. So I had to call it T instead. And this is, we're going to call this dimer T and this dimer D. So like if we're doing lithium 11, then this thing is lithium 10, and this is 2 neutrons, and neither of them is actually bound, but they both have very low-lying resonances. And for these purposes, we'll imagine performing a scattering experiment. So indeed, that's what we want to do. So let's imagine we do ND scattering. And as far as effective field theory treatments of this go, that was actually the original application. People had done ionless EFT, short-range EFT for the nucleon-nucleon system, and they wanted to do neutron-deuteron scattering. So you come in with a neutron on the deuteron, and this thing breaks up. So there are 2 ways it can break up. What are they? I'll help you with the first one. The first one is it can send its neutron over here, and then get that. I should say, like, we're going to assume that we are below the 3-body threshold, so that this state can't go on shell, so it can't just break up and go directly to a final state. Okay, so it can break up. What else? Anyone want to suggest something else that can happen? The dotted line goes across, good. All right, let's power count these diagrams. So this one here is like 1 over m, 1 over e plus minus, I'll just keep this very simple for now. It's a 3-body propagator. And so this is going to go like 1 over q squared. And the same thing is true over here. So we actually need to consider both of these mechanisms when we think about 3-body scattering. Of course, this one lands you in a different channel. Sorry, no, this one keeps you in the same channel. This one lands you in a different channel. CT, right? So this one takes us from the channel where we have a bound deuteron to the bound dineutron channel, with leaving the proton behind. So this means that we're going to have to think about this as a couple problem. We're also going to have to think about this as a non-perturbative problem, because if I go to one loop here, all the loops with an individual dimer are included in the shading, right? So I've already dressed my dimers. These are S-wave dimers. They're all fully dressed. But the only thing left that can happen is that the particles can go across to the other one. So I could have this mechanism, or if I continue, that's continuing this picture, or if I make the neutron bounce back to the other side, here, I will wind up back in the channel I started in. But if we power count these diagrams, the dimer propagator, whole thing here is a scattering amplitude, and at leading order, this goes like 1 over q. Yeah, I'll go up here so that people can see. The propagator goes like 1 over q squared. This propagator goes like 1 over q squared. This is a 3-dimensional loop. So this diagram goes like 1 over q squared. And if you work it out, this diagram goes like 1 over q squared as well. So you need to sum a set of diagrams here, a class of diagrams involving these. One of the people who worked on this problem early on called these the pinball diagrams, right? So these diagrams where basically either the core or the neutron is bouncing backwards and forwards. And if you work it out, all these diagrams are the same order. So you need integral equations because you need to sum that class of diagram, an integral equation. And you need integral equations because you have a, I'm sorry? Oh, from the loop, right? So this is integral d3p over this loop. Right, yeah, thanks. It was kind of quick. All right, so now it's your turn. In the remaining 15 minutes, I want you to think about the following. So we have an amplitude for ND goes to ND. So those are diagrams that start and end with a neutron as like the spectator. For those of you who have ever seen Faddeev equations, this is the spectator language, right? So the neutron is the spectator to this two-body system. And then I want to think about a different class of diagram, well, yeah, a different process really, in which the core is the spectator and we're going core CT to ND. There we go. All right. So let's see. 1, 2, 3. So the 5 of you in the back row, you all should work together. You 3 work together, you 3, because this is not an easy problem, right? So form groups of 3 to 5. And you can attack this problem however you want. Right? You can sit there and draw a bunch of diagrams and then see if you can organize them. Or you can try and think out how you could relate this process to this process in a general way. Either one is fine. Basically, you can think about it inductively or deductively. Inductively, like you draw diagrams and try and spot the pattern. But your goal is to have an integral equation. So this, let me get you started, right? So the leading order contribution here, what would be called the driving term in the integral equation, is the one that we worked out at first. But then there's going to be some other stuff where this is coupled back to itself, maybe. Maybe there isn't stuff where it's coupled back to itself, or it's coupled to the other one. And then there's some diagram that sits out here, and some other diagram that sits out here. And likewise, you want to write an integral equation for this one, which starts off with the leading mechanism that can transition you from this one to this one. And then has some, relates higher order diagrams to what happens inside the amplitude. Right? So this, just to be clear, right, this is meant to be an infinite sum of graphs. Right? So just like in the Lippmann-Schwinger equation that Professor Kaplan talked about on Monday, in the Lippmann-Schwinger equation, you say I have an infinite set of graphs. And you realize that if you define this infinite set of graphs as A, then A is equal to the first one plus the first one times the intermediate state propagator times A. So that's what we're trying to do here. We have an infinite set of graphs that contribute to this amplitude, and we're trying to figure out how to get back to the same infinite set of graphs so that we can write an integral equation for that amplitude. All right, so now that I've introduced the problem, you only have 10 minutes. That's okay. What I really want you to do is just have a go at it, and then we can talk tomorrow about what you all found. And then we can talk about, the good news is that once we have the integral equation, we have Feynman rules for all the elements, right? We can say that the Feynman rule for this is like minus I times the amplitude. We have a Feynman rule for the propagator. When these things appear in intermediate states, we have a Feynman rule for the dimer. We have Feynman rules for everything. So if we can figure out how to express this infinite diagrammatic series as an integral equation, we can write down the integral equation, and then we can put it on a computer and solve it. That's the game plan. But first, we have to figure out what the integral equation looks like. So go for it.